Video we looked at, what is an imaginary number and why is it really important? It's basically important because we didn't have a number to answer this question, the square root of negative numbers. So we're right here, the square root of negative numbers lead us to imaginary numbers. And don't disregard this number because it has the word imaginary in it. It's not a fake number. It's just a concept or an idea. And maybe you've never thought about it before, but numbers like 0 and -5 and even positive numbers like 2, these are all just ideas. So is I. I is an idea as well. But what's fun about I is we have this cool pattern to explore. Once we say that I equals the square root of -1, it's natural to ask, well, what does I squared equal? Well, that equals I times I. And what's that? Well, what is the square root of -1 times the square root of -1? If you think for a moment about the square root of any number, like the square root of 25 times the square root of 25, well, the square root of 25 is 5, and the square root of 25 is 5, so it's like 5 times 5, and that's 25. So the square root of any number, here was 25, but any number times itself equals the number that we're taking the square root of. So the square root of a times the square root of a is just a. Just like the square root of 25 times the square root of 25 was 25. So the square root of -1 times square root of -1 is going to be equal to the -1. And that's kind of neat because I squared, rational numbers that have this behavior, any positive or negative number squared gives you a positive number. But now we're dealing with square roots, and we're dealing with this number I squared is still negative. Well, what about I to the third power? You can think of that as I to the second times I to the first. This goes back to the rule of exponents. I to the second times I to the first equals I to the third. Remember, if the base is the same, we're just adding the exponents because I squared is I times I, and it's times another I, so that's 3 i's, right? And I squared, what we set up here, it's equal to -1. So it's -1 times I, which is just equal to -I. Well, what's -I equal to? Well, we could write it as -I or negative the square root of -1. I think, though, that I'm going to leave it as -I, just a little bit neater. So our pattern so far is that I equals the square root of -1, I squared equals -1, and I to the third power equals -I. And then we have, well, what's I to the fourth? You could think of I to the fourth, it kind of brings us back to our positive products. And this makes sense since it's equal to I squared times I squared. Well, I squared was just -1, and we know it brings us back to our rational numbers now. -1 times -1 is a positive 1. So I to the fourth power is the first time we get back to our positive numbers. And we can keep going with this, but I think we might see a pattern. And to complete the pattern, I'm going to go back a step in a moment. But anyway, so I to the fifth, what's that? Well, I to the fifth is like I to the fourth times I. So it's just 1 times I, and that's equal to I. So look at that. Already we came back to our first number, which is just I. So we had I equals square root of -1. Now we're back to that. And I think we should rewrite this pattern. Let's just look at this in a little bit neater of a fashion. What if we started with I to the 0? In other videos, I go over this, but anything to the 0 power, maybe we could talk about 0 to the 0 power, but any other number to the 0 power is going to be 1. So I to the 0 is 1. And look at the exponents here. I to the first is just I. I to the second is just going to be -1. I to the third is going to be equal to -I. And I to the fourth is going to be equal to +1. And I to the fifth, as we said before, is back to I. I to the sixth, well, now we have this pattern. And instead of figuring out I to the sixth, let's use the pattern. The pattern, we had 1, I, -1, -I, and then it starts again. 1, I, so the next pattern is going to be, next number, is going to be -1. And then I to the seventh is going to be the next number in the pattern, which is just again -I. and then I to the 8th is going back to the original number 1. So 1i, negative 1, negative I. So 1, that's the first step, then I, then negative 1, and then negative I. It's really nice that this pattern is going to recycle. So the pattern repeats or recycles every 4 numbers. Every 4 numbers. And this brings up some useful things. Well, if I to the 0 is 1, and it's going to repeat every 4, then this also equals I to the 8th. Oops, excuse me. Even before that, I to the 4th. As we saw here, I to the 4th is 1, which is equal to I to the 0. And then I to the 8th is also the same thing. So notice all we're doing here is our exponents are multiples of 4. This is 4 times 0. This is 4 times 1. Let me write it down. This is 4 times 0, and this exponent is 4 times 1. And this exponent here is 4 times 2. And that equals, well, now we have 12, or 4 times 3, and this is going to keep going. So all of these are equal. Okay, so if those are equal, if I to the 0 equals I to the 4th, and this keeps going, then it also means that I to the 1st equals I to the 5th, right? We're going up exponents by 4 each time, which equals I to the 9th. And if we look at I to the 2nd, our third step in the pattern, that equals I to the 6th, which equals I to the 10th, and so forth. I to the 3rd, the last part of the pattern, equals I to the 7th, which equals I to the 11th, and so forth. So really, we only need to figure out any I, and this is what's so fun about the imaginary numbers, we only need these 4 original numbers, which this pattern. And this is modular arithmetic, because we have a modular where it's repeating every 4. And what that means is that we could write them out like this to figure it out, but if I could give you something like, I don't know, I to the 114th, and it would be kind of tedious to figure out which group this falls into. So an easy way to do this is to look at the exponent and take the exponent and divide it by 4, right? To find out how many times does this pattern of 4 fit into the exponent 114. Well, 114, well, I think of 100. 100 divided by 4 is 25. And then there's, so 23 times 4 is 112. Oh, 28, excuse me, 28 times 4, because 4 times 20 is 80, and 4 times 8 is 32. It's 112, which means there's a remainder of 2, because we want to get to 114. So all we have to do is look at our remainder. So this pattern of 4 goes into 114 28 times, and then with 2 left over, which means that, well, if nothing was left over, the answer would be I to the 0, right? 0, nothing left over. If 1 was left over, then it would be I to the 1st. But if 2 is left over, right, remainder of 2, we have our step in the pattern I to the 2nd, which is our, let me use a bigger color, bigger pen here. Here's our 0 step, our first step, and our second step, right? So that's the remainder of 2. So I to the 114 actually equals I to the 2nd. And I to the 2nd is just equal to negative 1. So this equals negative 1. Let's look at another example. If I gave you I to the 12th, we take 12 divided by 4. Well, 12 divided by 4 is just 3, and with the remainder of 0. So I to the 12th, and we might have even said this before, equals just I to the 0. Right? We're matching those remainders. And that is equals 1. And if we had I to the 102, or 103, let's say, that equals, well, 103 divided by 4 equals 25, remainder 3. So this equals the third step in our pattern. And our pattern was we had 1, 1, I, negative 1, negative I. So actually, and then that was I to the 3rd, I to the 2nd, I to the 1st, and I to the 0. So actually our third step, our last step in the, our fourth step in the pattern is our remainder of 3. So we match those remainders. This equals negative I. And again, if you think about the steps in the pattern, you're starting here. So your first step, second step, third step. which is why if we have a remainder of 3, it's equal to our third step. You're never going to have a remainder of 4 because we're looking at division by 4. So there's either going to be no remainder, right, our starting point, 1 remainder, 2 remainder, or 3 remainder. And that's, I think, essentially it for what's happening here with the number I. Oh, actually, there's a lot more to say, but this is a good starting point.